Yeah.
Okay.
So then please go ahead.
Okay. So good. So I have no idea. This is probably not. Hopefully not going to be that long. This is one of the. Actually, this is the first time I'm talking about this paper. So I did not have the usual accumulation of a million slides from previous talks. So I'm going to talk about the paper that we wrote with Meijian Li and Xingbo Zhao. We put it out a few months ago, and this is most of all I have to say is Meijian Li's work. So that somehow she's the main person doing the actual work, and still is. We're continuing on a further project which I will discuss in the end. Also, some of this actually started from a paper that Meijian wrote before she came here. So Meijian was at Iowa State, and she somehow started working on this kind of things already there with Xingbo and a bunch of other guys who are part of kind of the Iowa State group. Okay. So, and yes, okay. And Meijian is now still in Jyväskylä, but she's going to move to Santiago in January. She's part of the semi-annual ERC postdoc migration. Now that my ERC is finished and Carlos is going strong, all my postdocs are moving to Santiago, and maybe they will someday come back here. Who knows? Okay, so first I talk about the motivation, motivate why we are doing what we're doing. Then I'll try to discuss in not very mathematical terms what we are doing in this paper, and then I'll show some colorful pictures made by Meijian demonstrating results. And so far this paper is really about developing a code and a formalism and testing that the code does what you think it should be doing, that it behaves in a way and that you understand what it's doing, why it's doing like that. And in the hope that this will be something, a tool that can be used to do some actual physics later on. So later on I will just briefly mention at the end. But so far this is really just writing a code and testing the code. And there's a lot of interesting. I've been teaching quantum mechanics too now, and then and somehow doing old-fashioned quantum mechanics, time-dependent perturbation theory. And one of the fun things about writing this paper is that the things that you teach when you're teaching things like the golden rule, Fermi's golden rule in advanced quantum mechanics, or somehow just perturbation, time-dependent perturbation theory. And this is a calculation that explicitly does that. It's a non-perturbative calculation, but where you can explicitly see somehow that what is happening in somehow just this kind of a textbook quantum mechanical system in some sense. So a lot of fun thinking about different interpretation here. Okay, so the physics case. I am now thinking of as a motivation for doing what we're doing, two situations that appear in high energy QCD. One of them is scattering that I call a finite square root S. Now the background here is that, so I come from a background of small x physics. So small x physics meaning high energy collisions, calculating cross sections. That somehow, in addition to the classical Yang-Mills, most of what I have been recently working on is really high energy cross sections, CGC cross sections, BK equation, electron ion collider physics. So the physics case is dilute dense scattering, for example, electron nucleus scattering. So a very dense object made of gluons, like a heavy nucleus, and then a dilute probe, like an individual quark or a quark anti-quark dipole from a proton at high X, or an electron which emits a photon, and a virtual photon splits into quark anti-quark dipole. So a dilute colored probe measuring the dense color field of some high energy nucleus-like object. Okay, so what people in the CGC community typically do is that you make your life simple, as of course you always want to do in physics, And you take the, if you want to study things that happen at high energy, you make the approximation that the energy is infinite. Okay, because that actually turns out to simplify your life a lot. So a lot of the somehow the calculations that people use in this context, small x physics, are really in and I will come back to this Lorentz boost a little bit more, but are done in the iconal approximation, where what the scattering is. The scattering is this dilute probe, a quark, for example, that goes through an infinitesimally thin shock wave of a classical color field. So infinitesimally thin, and somehow the infinitesimally thin shock wave is really a result of the high energy approximation, because if you're at high energy, you can go to a frame where your target is moving fast against you. If your probe is going at high, you can boost to a frame where the target is moving fast, and then target is moving fast, and then the target is Lorentz contracted so that it's infinitesimally thin. And since physics is boost invariant, it means that somehow actually, I mean, you can always decide to go to such a frame. So you always often do calculations with a target that is a delta function, thin delta function in the longitudinal direction that you're going. But in reality, of course, given a finite amount of money to build a collider, you are going to do collision experiments with a finite square root of this. So this is an approximation, and one would want to have systematical ways of going beyond this approximation. And then there's some physics that really do not happen in the large high infinite square root S limit at all. Like the physics of spin is physics that is suppressed by powers of the collision energy. So for example, if you want to study the physics of spin, which is a big part of electron ion collider physics, for example, you want to be able to calculate things where the collision energy is finite. So you need sub-iconal corrections. So you need, depending on the Lorentz frame you work in, you need corrections where your probe particle does not have an infinite energy, or equivalently, where your target has a finite thickness. It's not a delta function anymore, but you go through a finite thickness target. So this is one physical situation. The other physical situation, of course, is the one that you are much more familiar with than I am, which is jet quenching, where the basic idea is similar. So you have a high energy colored particle, let's say a quark, for example, which is born in a high virtuality collision in the early stage, in the beginning of a heavy ion collision. And then this high energy particle, this quark, which is going to become your jet, traverses through an extended region at high energy, an extended length region of matter that has color charges, and then it is modified and radiates and so on. And you would want to track this time dependence of this particle as it goes through this system that has color charges. So we'll just model this system by a color field, a particle going through color field and possibly emitting gluons. So in both cases, what these have in common is that what you would really want to do is that you want to study things explicitly as a function of a light-like time coordinate. So we really have light-like massless particles that are going at velocity of light. So the trajectory of the particle we are interested in follows a light-like trajectory. It's not really a time-like or a space-like problem. It's a light-like trajectory of this particle. So the method of choice here that we want to use to describe these kind of systems is that somehow if the physical situation is that the particle that you are studying follows a light-like trajectory, you want actually to do quantum mechanics and quantum field theory in such a way that you choose this trajectory of your massless particle going at the speed of light as your time coordinate, and you somehow build the whole formalism in such a way that your time coordinate is not t. Your time coordinate is the coordinate where you following the trajectory in space-time of your massless particle. So this is why you would want to do light cone quantization. So light cone quantization is just this. Okay, so it's quantum mechanics with a light-like time coordinate. So let's discuss a little bit somehow more the time scales here. So one of the unfortunate things is that you cannot trust any 2 or square root 2 in my slides, because me and my co-authors have a different convention concerning square root 2s. And so you should not trust any factor of 2 or square root 2 here. Fortunately, there's not going to be many in these slides. So what the coordinates are x plus, which I will consistently call time. So this is the light cone time. This is the trajectory of a particle going at the speed of light in the positive z direction. The other combination of time and z coordinate is x minus, which is a coordinate. It is a longitudinal coordinate, longitudinal light cone coordinate. So x plus is time, x minus is a not space-like, but it's a spatial coordinate. Okay, and then transfers. There's two directions that are transfers to the z-axis, which are transfers to the particle, that high energy particle we're interested in. So what kind of different length scales does one have in the problem? First, you have a particle that is going through some extended medium. So target of size L. So this is the length of the target in x plus coordinates. So it's a plus. One of the things that is nice about these x plus and x minus is that when you boost in the z direction, these behave very simply under a Lorentz boost in the z direction. So since it is a upper plus component, it means that if you boost the whole system, if you boost your whole system, both your probe and your target, actually it's a length in x plus. So a length in x plus in a Lorentz boost gets multiplied by a Lorentz gamma factor. Okay, so and you want to have a boost in, and for a high energy collision, what you want is to have a description that is invariant under such boosts. Then there's a transverse momentum squared you get per unit length of medium, which is q hat in the jet quenching literature. This is denoted by is the q hat parameter. It tells you that when your high energy particle is going in the z direction, but it also gets kicks in the transverse direction, and depending on how long it goes in the medium, it gets a certain amount of kicks. So since this is a transverse momentum per unit length, and length is not boost invariant, so the q hat is also not boost invariant. It is boosted by, it also changes when you go to a different Lorentz frame. On the other hand, one thing that is boost invariant is the total transverse momentum you accumulate when you go through a medium of certain size in x plus. This is denoted by q squared, so saturation scale squared. And the reason is that, so saturation again refers to the high energy scattering. So the reason is that if you have a finite target and you have a very high energy, the only thing that matters is this accumulated transverse momentum. So if you have a physical situation where the only thing that matters is this total integrated transverse momentum, when you go through a finite slice, then you can go to the limit where you just describe it as a shock wave. So this is kind of the quantity that survives going to the limit where the target is just a infinitesimally thin shock wave, the total transverse momentum. You have the probe has some momentum, so longitudinal momentum. A q plus meaning energy plus z moment, energy plus pz. So that when you boost to higher, when you boost, you increase the energy of this longitudinal probe. The momentum also has a light cone energy. What is light cone energy? Light cone energy, K minus is light cone energy. Why is it light cone energy? Because it is the Fourier conjugate to x plus. And what the definition of what is energy? Energy is by definition the quantity that is conjugate to time. And if x plus is your time, then K minus is by definition your energy. So K minus is the light cone energy. And I don't know if you're familiar with these. You might or might not be, but a simple calculation with this coordinate system will show you that the minus K minus, the light cone energy, goes like K. This boldface case is transverse. So K minus goes like K transverse over K plus. And there might or might not be a factor 2 here, okay, depending on your conventions. And that's somehow, I don't know if you get lost with these, ask me. Some people might be familiar with these and some people might not, and I somehow did not write all the relations down here. But so for an on-shell particle with a transverse momentum K perp and a plus momentum K plus, the on-shell minus momentum is given by K perp squared over K plus. So if you boost this, it has a minus, so it will be, if a plus component grows when you boost, a minus component will decrease when you boost, in such a way that plus component times minus component is boost invariant. Okay, so since this is a light cone energy of a fluctuation, by fluctuation I mean that somehow there's some kind of you have a quark, for example, and it fluctuates into a quark gluon state. Okay, so that's kind of a quantum fluctuation in the state of your particle. And then there's the lifetime of this fluctuation, which is the inverse of its energy. So 1 over K minus, and if you boost, it will be in a frame where it moves with higher energy, the lifetime will be longer. So of course, none of these things, most of these things individually are not boost invariant. So one should think rather in terms of ratios of things that are boost invariant, such as what is the lifetime of some quantum fluctuation compared to the length of the target. Here the gamma factors cancel, and this is K plus over size of the target K perp squared is a boost invariant combination that describes what is the ratio of the lifetime of the fluctuations versus the length of the target. Transverse momentum of the fluctuation, somehow, for example, a quark splitting into quark gluon with have some relative transverse momentum. How large or small is that transverse momentum related compared to the total transverse momentum you accumulate from the whole target? That's a meaningful comparison. The lifetime of such a fluctuation versus whatever is the intrinsic correlation timescale of the target. Again, a dimensionless ratio is a meaningful Lorentz invariant quantity to look at. So what we want to do is that we want to have an explicit non-perturbative numerical calculation, which allows you to go to very different regimes of these kind of ratios of length scales. Okay, and this is that's somehow what the interesting physics in this calculation is that you want to have a framework that is capable of describing very different regimes of this kind of ratios, and then hope that there's going to be, there should be a lot of interesting physics to study with such a framework. Okay, so I said we want to do this in light cone quantization. So what is light cone quantization? So you're more, to some extent, some of you more, some of you less, you're familiar with normal covariant field theory. So you have seen Feynman diagrams, Feynman rules, maybe or maybe not, you have taken a course in field theory where you derive these Feynman rules, but at least you have seen the diagrams and you know that every Feynman diagram corresponds to some algebraic expression for a scattering amplitude, for example. So what we want to do here is light cone perturbation theory. So the way you should think of it is that it's a different formulation of relativistic field theory, which has advantages and disadvantages compared to the covariant Feynman perturbation theory. And well, yes, advantages, disadvantages. It has disadvantage. This disadvantage is that it's not covariant. We are specifically choosing a very special direction in space-time. We are choosing the one out of the 3 coordinate axes as the z-axis, and we are treating movement along the z-axis very differently from movement along the 2 transverse axes. So we are explicitly breaking rotational and Lorentz invariance. But the advantage is that it is easier to maintain boost invariance along this direction. And the advantage is that sometimes if you're studying a physical situation, like this high energy scattering, well, the physical situation that you are studying already breaks boost invariance. The beam axis is a very different thing than the transverse axis in a high energy collision. So sometimes if the physical situation already breaks this kind of invariance, maybe you want to choose a theoretical description where you don't care about three-dimensional rotational invariance that much because your physical situation breaks it anyway. So that's what we're doing here. Okay, so then the rest goes like kind of in some sense, not like field, not to some extent like in field theory, to some extent like you would do in an advanced non-relativistic quantum mechanics course. You have your fields, your spinor fields, and your gauge fields, your boson fields. You say that your field is a linear superposition of field operators, creation annihilation operators. These creation annihilation operators obey commutation rules, and now one needs to be precise, they obey commutation rules at equal x plus. Whereas what you usually do in your lecture courses is that you have commutation rules at equal time. But here they are commutation rules at equal light cone time. Okay, so now you have creation annihilation operators. Now you can write down a Fock space of states. So you have vacuum, you have, and then this creation operator, with the creation operators, you can create particles in this vacuum. So you can have one particle, two particle states. These are known as the Fock. The space of this such state is known as the Fock space of states. One additional thing that you has it again advantages and disadvantages and somehow goes together with this picture. It's kind of a slightly distinct thing that, but you always want to do it, is that in addition you want to fix the gauge. So you want to fix the light cone gauge for the gluons. Light cone gauge meaning that the plus component of the 4-vector potential A plus is 0, so an axial type gauge. And whenever sometimes in some field theory textbooks you might see somebody describing what an axial gauge or axial type of gauge is. It has advantages and disadvantages. The disadvantage is that some calculations, like loop calculations, become messy because your gauge condition breaks Lorentz invariance. The advantage is that you can completely eliminate the redundant gauge degrees of freedom. And then it turns out that instead of the 4, in this formulation, instead of the 4 components of the gauge potential, you actually eliminate one by the gauge choice. Another one is eliminated by a constraint equation. And then you only have explicitly only two free independent components of the gauge field, which you can identify with the 2 physical polarization states of gluons or photons. So the advantage is that you're explicitly only working with physical degrees of freedom. You have no ghosts. You have no somehow negative norm states. You have 2 physical particles that are your gluons with spin up or spin down. Okay, so a somehow clear physical picture at the expense of some pain in calculations. Then what you do is that even my title is Hamiltonian Formulation. So Feynman covariant perturbation theory, you work with a Lagrangian. So you write down a Lagrangian, it's Lorentz invariant, then you derive Feynman rules from the Lagrangian, and everything is covariant at the same time. And what we do here is that we want to explicitly follow time development. We have chosen a time coordinate, which is special, and we want to follow things as a function of that time coordinate. And we want to somehow think of physics as an initial value problem, where you know the initial condition and you want to see what happens when you go forward in time. For such a situation, actually, you don't want to work in a Lagrangian formulation, but you want to work in a Hamiltonian formulation. So you want to take your Lagrangian, do the standard thing, which you learn in mechanics, and write down a Hamiltonian. And now a Hamiltonian, I recall that because x plus is energy, the Hamiltonian is actually k minus. So the Hamiltonian is the minus component of a 4-vector, not the 0 component of a 4-vector. So you do your standard thing and you derive a Hamiltonian. This Hamiltonian for my system is going to be like usually in field theory in particle physics. It's going to consist of two parts, the free part and the interaction part. The free part is just the part that is quadratic in these field operators. And the field part just has kinetic energy of particles. So every particle, quark, gluon, whatever in the Fock space has a momentum, 3 momentum, so K plus and K transverse. And to these three components of the 3 momentum corresponds in energy and on-shell energy. So the free part of the Hamiltonian is just the kinetic energies of the particles. And then there's the interaction part, which is 3 and 4 point functions of the operators of the creation annihilation operators. So that has the interactions of the theory. Okay, and once you have a Hamiltonian, then again you do what you would do in non-relativistic quantum, exactly as you would do in non-relativistic quantum mechanics, except that now your time is x plus, and you're doing something that is relativistic. But somehow you're using the calculation is organized as you would organize a non-relativistic calculation, except that now you're doing a relativistic calculation because your time coordinate is a light-like coordinate. So you have your Hamiltonian. You can write down an initial condition and solve the time evolution from your Hamiltonian like you would in elementary quantum mechanics. So as you learn in quantum mechanics, there's different ways to do it. You can use the Heisenberg picture, where states do not depend on time, but operators depend on time. You can use the Schrödinger picture, where operators do not depend on time, but states depend on time. Or you can use something that is between, and that's what we're going to do here. So we're going to use the interaction picture, where both states and operators depend on time, but in a different way. The interaction part of the Hamiltonian generates the time dependence of states, quantum mechanical states. The free part of the Hamiltonian generates the time dependence of operators. So both operators and states depend on time. The interaction causes states to develop into other states, and it makes the states depend on time. And then the free part of the Hamiltonian just makes operators depend on time. So this is why here I write that an interaction picture state, the time dependence of an interaction picture state, I stands for interaction, is given by the interaction picture interaction. So the interaction picture interaction part of the Hamiltonian. The interaction picture part of the interaction Hamiltonian, the interaction picture interaction, is given by the original interaction in your original Hamiltonian, and then an additional time dependence given by the free part of the Hamiltonian. So this kind of, with what we can, this part we call phase factors here, so that the interaction term gets rotated in as you go forward in time by the free part of the Hamiltonian. And this is, if you go to a good quantum mechanics textbook, which has the interaction picture, you will see exactly these same things. These are familiar to most of you. And the only thing that is different here is that the time is x plus and not t. But in terms of quantum mechanics, it's the same. So this phase factor, I will show a lot of things with and without this phase factor, because that is kind of one of the things that it is nice to have explicitly here, because what happens is that this P minus the kinetic energy is absent in the Eikonal limit. So because when Q plus in the Eikonal limit, when the energy of somehow very weirdly, again, this is light cone. So when you go to the high energy limit, the energy goes to 0. So the high energy limit in a scattering process is where the plus momentum of your incoming guy goes to infinity. And that means that it's minus momentum, i.e. light cone energy goes to 0. So in the high energy limit, your incoming particles have 0 light cone energy, or all your particles have 0 light cone energy, because P minus goes to 0. And this phase factor drops out. And then you have something which is completely somehow coherent. And then going away from the iconal limit to finite scattering energy, finite square root S, brings in this phase factor, which somehow makes things decohere.
Sorry, Thomas, this limit is cute because, right, it's kind of like a non-relativistic, this P minus is a kind of a non-relativistic energy.
Yes.
And the Q plus to infinity means that you basically have infinite mass, right? So
yes.
basically you're just stuck there, and then and you're boosting together with it.
Yeah, actually this is a somehow it is like a two-dimensional non-relativistic system with two transverse dimensions. Energy is momentum squared over K plus. So K plus plays the role of a non-relativistic mass, and K minus the role of a non-relativistic energy.
Yeah.
And it is, and somehow one can take this into a formula. There's a Galilean invariance. Somehow you have a boost invariance under longitudinal direction, and then a two-dimensional Galilean invariance in the transverse plane. So somehow it is something that is you're combining a picture where you have in the longitudinal direction boost invariance, so very relativistic. In the transverse direction, mathematically speaking, it looks like non-relativistic. It looks like Galilean physics, not Lorentz invariant physics. So it's weird, but for a physical situation where you have high energy, it is kind of the good way of thinking about things. Good. So this is the system we want. So this is the way we want to formulate our system. We have an interaction part of the Hamiltonian. We have a free part of the Hamiltonian. We have quarks, gluons in a Fock space of states. Okay. So then a little bit more physics ingredients. What we do. First of all, we study the scattering of some quark gluon system from a target. The way we describe this target, it could be your medium in your jet quenching problem, or it could be the target, the proton gluon part, gluons in the proton at in a high energy scattering. We describe them here by a classical background color field. So this is a background field. It doesn't feel anything. It just pushes the quantum particles around, but there's no back reaction to the classical background field. For the purposes of this work, we use the MV model. So the MV model where this field you get from a color charge density, which is a random variable in the transverse plane and in the longitudinal direction. So you have randomly placed fluctuating color charges. It's kind of a very minimalistic assumption about somehow what a colored medium could look like. Random color charges, and there's one parameter, which is the density of how many of these color charges you have per unit volume. And then they're completely uncorrelated. At each point in space, they are completely independent. Each point in space is completely independent of each other. Here now we are using sneakily a leading high energy approximation, because we are taking our target field to only have a minus component. And that is justified if you have a high energy probe. So we are not kind of here fully going to all possible non-iconal corrections. But of course, this is something that one could generalize. It somehow I don't think it would break up anything else about the structure of our calculation. It would just be a little bit more complicated to generalize this. Why is a minus component the leading at high energy? If you have a probe, somehow the coupling of a charge and a color field is a current J dot A. It's a J dot A, current times gauge field. And if you have a high energy if you have high energy particles, basically the current should be proportional to the momentum of the particles. So of a system of very light particles going with high velocity, close to light velocity, their color current should have one big component, which is the plus component. And therefore, it only couples the color current of high energy particles only couples to one component of a color field, which is the minus component. So we're only taking the component that has the high that is most strongly coupled to a high energy colored thing. Okay, so some kind of a high energy approximation here. Then what we do, we really want to do an explicit numerical calculation. So we have our we have a discrete lattice in space-time, in space. On a transverse lattice, we go up to 32 squared points in the transverse space. And this transverse lattice can be a momentum space lattice, discrete momentum point modes, which we need for the quark gluon emission and absorption, because that is something that is kind of naturally happens in momentum space. On the other hand, by a Fourier transform, you can always go between momentum and coordinate space. So this lattice is also a lattice in coordinate space of the order of 32 squared points in coordinate space. And that is convenient for interacting with the background field. Okay, and we constantly Fourier transform back and forth with these, because the momentum, one interaction is natural in momentum space, the other one is natural in coordinate space. We have we also discretize the x minus coordinate, which means that we have put the x minus coordinate, in a finite periodic interval, which means that we have discrete modes in Q plus, in the plus momentum. For bosons and fermions, we have periodic and anti-periodic boundary conditions in x minus. So this means that for bosons, we have integer modes, and somehow fermions, we have semi-integer modes of discrete longitudinal momentum Q plus. We leave out the zero mode, which we would not know what to do with. The zero mode is one of the trickier things in light cone perturbation theory, why somehow a lot of sicknesses hidden there. So we just leave it out. It's a kind of discrete calculation. We can decide what modes our system has and what modes it doesn't have. And it's we can just leave it out. Because we assume that our background field is independent of x minus, the longitudinal coordinate, longitudinal spatial coordinate in this light cone time, it means that the total plus momentum of our system of particles is conserved when you interact with this kind of a background field. Again, something one could give up in principle. It would just make the calculation more complicated. It's not a fundamental thing, but it would just be a pain, but in principle could be done. Okay, so we discretize the system, put it on a computer, and then we just solve the equation of motion. We have our state at a next time step, which is given by the state at the previous time step, and then interactions, whatever interactions we have in our Hamiltonian. So quark emission, quark absorption, gluon emission, gluon absorption, and then interaction with the background field. So in this work, this is because we are still just somehow testing what our code does, we will almost always choose an initial condition where at time x plus equals 0, we start with a state that has purely one quark with 0 transverse momentum and some given longitudinal momentum. So it's we start with a state which is a one single quark state, and then see what happens to this single quark state in time. Now, of course, it's impossible to solve full field theory, so we need to do some approximations. The approximation we do here is that we truncate the Fock space, and we are working explicitly in a Fock space. We truncate the Fock space to have only quark and quark gluon states. If you're working on a and going to higher orders in this truncation is very expensive, because somehow a 3-particle state is a tensor product of 3 1-particle states. And if each 1-particle state has 32 squared momentum modes, a 3-particle state would be 32 to the 6th momentum, transverse momentum modes. So it gets going higher in this Fock space truncation, gets expensive very fast. Unfortunately, that is a limitation of this approach. So our Hamiltonian schematically consists of we have 2 sectors, quark sector and quark gluon sector. both sectors within themselves have an interaction with the background field. And then you have transitions between the sectors. A quark can emit gluons and become a quark gluon state, or a quark gluon state can absorb a gluon and become a quark state. So we have a perfectly well-defined finite dimensional, because discretized finite but large dimensional system with a Hermitian Hamiltonian that conserves probability. This is why if you have emission, you should have absorption. Otherwise, you don't have hermiticity and probability is not conserved, and then you quickly lose idea of what you're doing. So this is our Hamiltonian. And the background field is treated in coordinate space. The gluon emission absorption is treated in momentum space, and we're going back and forth between these. And on periodic transverse lattice, some tricky issues related to that, which I will only talk about if you ask. Okay, so first test, no background field. First, we turn off the background field. No background field interaction, so only gluon emission and absorption. Here's the probability of being in a quark state, the blue line. And then in different longitudinal momentum split QG states. Of course, the total P plus is conserved, but that P plus in a quark gluon state can be split between the quark and the gluon in different ways. And they have slightly different matrix elements, so there's a different probability for each of these. Depends also on the mass. We put a small quark mass to regulate things. So on the left is without this phase factor. So this is kind of the infinite energy limit in some sense. And what you see is that, of course, it's a two-state system. It can't do two-state, but kind of a two-state like system with transitions from one state to the other. So eventually what you develop is that you have as a function of time, you have an oscillatory probability. You oscillate between your quark state and your different gluon state, and then you oscillate back. And this happens completely coherently for as long as you want, because the Hamiltonian is Hermitian, just oscillates forever. This is like a Rabi oscillation. In quantum mechanics, this kind of a thing is like a Rabi oscillation. A Rabi oscillation is a 2D system, a two-state system here. It's a slightly more complicated, but not much more complicated in the end. If you do put the phase factor, what happens is that when you go from the quark state to a quark gluon state, the quark gluon state has a slightly different energy. So it's oscillating with a different phase, this P minus X plus phase. And eventually, and somehow the phase, which is the oscillation frequency, is basically this frequency here. So eventually, this phase causes you to decohere. And then you actually end up being in some state. This is basically kind of a Fermi. If you look up the derivation of the Fermi golden rule in a quantum mechanics textbook, this is kind of the way it happens. You have an oscillation which eventually things that are not allowed oscillate so fast that they just decohere. So this is a very explicit demonstration of this issue of decoherence. It's really somehow there are numbers and you can plot everything that you want. These plots are kind of just integrated or transverse momentum. So because it's different transverse momentum modes, it's a little bit difficult to somehow know, okay, what is the transverse momentum that gives the scale? It's basically close to the UV cutoff for these figures. But of course, you could do this differentially if you want. This is just somehow, you have to decide what to plot. Here's what things look like in momentum space, transverse momentum space now. Here's our quark in the quark sector. So of course, since we have no background field and total transverse momentum is conserved. So you start with a quark with 0 momentum, you end up with a quark with 0 momentum, nothing happens. Then there's the QG state. So the momentum is conserved. So the momentum of the quark in the QG sector is always opposite to the momentum of the gluon, opposite with the appropriate P minus weight. So opposite in the appropriate way, okay? Weighted with a 2D mass like P plus, whatever. Interpreted in the right way, it's the opposite. And then actually the matrix element for this emission grows with transverse momentum. So the most likely states are the states with a large relative momentum between the quark and the gluon. And of course, the quark and the gluon have opposite momentum. So of course, these plots look exactly the same. When you include the phase factor, of course, the phase factor basically gives you an exponential of p perp squared over p plus times x plus. And if you look at this at a fixed x plus as a function of p perp, it looks like this kind of a densening oscillatory pattern as a function of p perp at fixed x plus. You don't usually look at a phase factor, like you usually look at this, think of this as an oscillation as a function of x plus. But of course, you can also plot it for a fixed x plus as a function of p perp, and this is what it looks like. And so you have oscillations because of this phase factor. And what decoherence is that these oscillations average out to 0. And then in the end, when you wait for a long enough time, only the 0 mode survives, because all the in principle, these high momentum splittings are enhanced. But once you average over these oscillations, they average 0, and energy, in some sense, energy is conserved, and then these high relative transverse momentum transitions are forbidden in the end if you wait for long enough for decoherence to do its thing. So again, kind of things that you can see in a textbook calculation, but here they are very explicit, and you can make a plot of what happens. Then let me turn off gluon emission and absorption and only have a background field. So now the background field, kind of what it does is that it depends on space. It depends on transverse coordinates. So it pushes particles around. It gives transverse momentum kicks to particles. So I start with a quark with 0 momentum, but in the end, I end up, after some time, I end up with a quark which has some finite transverse momentum, given by basically QS squared. Is the typical momentum spread here. Here, I'm not allowing transitions. I just turned them up by hand. So I put in some, so we put in some initial quark and initial Q state in the QG state, just to see that they also get their transverse momentum kicks. If I do this in the weak field, for a weak transverse field, I can still see some of these round patterns from the phase factor. But then if I make the field stronger, kind of the phase doesn't matter anymore. And I just see this momentum broadening by the background field. One way to parameterize the field strength is to calculate what is a cross-section. So here I put cross-section in quotes, although it is defined as explicitly the way you would define a cross-section. It's not really, in this case, a very physically meaningful quantitative calculate. In particular, it's not infrared safe. What would be infrared safe is a differential cross-section for getting a certain PT kick, but the total cross-section here is not infrared safe. But anyway, we have a model where it's on the lattice, it's regulated, so we can actually calculate it numerically, and we can calculate it analytically. It's given by the expectation value of a single Wilson line. So this is another way of seeing that a single Wilson line expectation value is not a color singlet. It's not going to be infrared safe. And consequently, it goes like exponential minus 1 over mg. Mg is a cutoff. You would, in principle, want to take mg to 0. But if you do take this mg to 0, then you get exponential of minus infinity, and you get exponential of minus infinity, and then you get a cross-section of 2 given by this 2. But it is just not really physically meaningful, but it's a good check of the numerics that, okay, our points have some scatter, but they are more or less lie where we suppose that they should be. This is for quark. You can do the similar thing for quark gluon. Good. Then the full simulation. So now I turn on both interaction with the background field and the emission and absorption. So you see both the background field is giving you some momentum kicks. You have emission and absorption. You start with nothing in the QG quark gluon sector, and you develop something in the quark gluon sector. You have this phase pattern oscillation from the phase pattern, and then you have momentum broadening. Here the field is pretty weak, so you don't see that much here. If you make the field stronger, the field starts affecting what you have in the QG sector. Again, somehow you can plot what you want. So there's a million things you could plot. This is just somehow some choice that we made. Again, here are the probabilities of being in the initial quark state, in some different quark state, and in the QG sector. If you don't have the phase, you would just oscillate. But when you have the phase, you start with a quark only. After some finite amount of time, you basically end up in a relatively static state where you have some quark component and some quark gluon component. And then gradually, because the momentum is diffusing, you gradually develop a larger and larger probability of being also in some other total transverse momentum state, which for these particular values of the parameters, kind of this total transverse momentum accumulation is much slower than developing this QG cloud.
Toumas,
yep.
On the previous plot, what
Sure.
I'm curious that that can I see the fact that once I have this dipole, and depending on the size of the dipole, the medium will act on it in different ways. Is this the ups and downs in the middle plot?
This is in momentum space, so you cannot really see the size of this coordinate space size of this thing. What you can see more easily for the quark sector here is that you start with the transverse momentum 0, and then after you interact with the background field, with some probability, you have a non-zero transverse momentum. If you would, of course, this is another place when one really has to take the uncertainty principle here seriously. Here we chose to start with a fixed transverse momentum state. And this means that by the uncertainty principle that this quark in coordinate space is completely delocalized. This quark is everywhere, right? And so if I would make a plot of somehow the transverse space, it would not be, it would just be flat, so it's hard to see. Here, I think if you think of relative separation, you could dig it out from here, but I don't think it's something you can really see on this plot. This is a momentum space plot. So somehow you have a quark and a gluon with a relative momentum separate from each other. Somehow you would need to, this kind of a plot, it's a little bit difficult. You would need to Fourier transform in your head to have a coordinate space picture. So I don't think you can see it in this picture in the way that you maybe want.
I think in some way you can maybe see it in this limit of, again, a kind of a high energy limit, but keeping the ratio of transverse momentum to energy constant or something like that. You would assume that so the angle is constant somehow. So then somehow the classical trajectory would in coordinate space would be very much peaked around your expectation, which is that it's just PT over P plus times time, basically. So in some limit, it's
yeah. So in this sense, the classical trajectory is kind of the classical trajectory. This is there's a phase. So somehow the classical trajectory is kind of thinking of these as waves that are propagating, and then you, in order to follow the classical trajectory, you have to sit on top of the wave and follow the wave.
Yeah,
that's the classical. So it's kind of in some sense following these circular waves.
Yeah,
actually, these are incoming circular waves now in this but somehow, yes. These are incoming because it is x plus is it's an exponential of something times x plus, and when x plus is higher, x plus is increasing. So in transverse momentum space, they are going in.
Mm-hmm. So this question here, this different Q is just a quark that has somehow flipped over to another momentum state. Is that so? You have the initial quark has kind of explicitly transverse momentum 0.
Yeah. So the initial, and then you have interacted with the background field, and the background field has kicked you. and then you end up with some other transverse momentum.
Mm-hmm.
And
So
this
the-
kind of, and this, in some sense, you can see that here, this is the blue, that happens at some rate, which is determined by the background field parameters. And this, of course, we can vary these rates of how efficient the background field is versus how efficient splittings and mergings are. This is just done with some specific parameters without thinking about too much of which regime we're in.
Do you have color here also? Is there a color state? There's
a color, yes. So we keep track of the full color. I mean, there are plots in the paper. I didn't put them here because it's a little bit hard to see. But the quark has three colors. The QG, in the QG sector, the quark gluon state has 3 quark colors and 8 gluon colors. So altogether 24 colors. So in the QG sector, there's 24 different color states. And this is what is plotted here is the sum of the probabilities to be in this any one of these 24 color states. But then of course we have checked that somehow if we put the incoming quark in color state 1, only specific gluon emissions are allowed. The gluon emission has to end up with a quark gluon state in the same color state as the incoming quark. But then the background field can give you color. So the interaction with the background field will make you go from one color state to another color state. And that's basically what this thing measures is that if the background field strength is 0, here you are staying, the quark is staying in the same color state that it came in with. And here, when you go to this stronger field after the scattering, the quark has complete, in this case, to some extent, of course, it has lost its momentum. It has gone to a different momentum state also. But because this is kind of this infrared unsafe total cross section, so most of the cross section here is actually the quark not actually getting any momentum but changing its color. And if your outgoing quark has a different color than the incoming quark, that counts as a scattering. But it's a scattering with 0 momentum. It's kind of maybe not a scattering you're interested in physics from the point of view of physics, but in the formal definition of the cross section, that counts as a scattering. And we can follow we can follow these explicitly color by color if we want. Good. So this is a relatively weak field. This is a much stronger field where you see that, okay, pretty soon you're actually being kicked into some other total transverse momentum state. And then the probability of somehow really staying in this initial quark state vanishes very fast. And even without the phase, because the background field is efficient, and with the phase, somehow these oscillations are very efficient. Okay, so there's a couple of other plots in the paper with different looking at different things, but these are the ones that I wanted to show here. So just as an outlook for the future, of course, what we're doing now is to actually, as a first thing, to somehow try to formulate this for the physics case of a finite energy scattering, sub-iconal corrections to scattering. Now, all of the calculations I showed here were starting with a pure quark state. Now, that is actually not the correct initial condition. So I think basically our algorithm is already there to study the sub-iconal scattering. We're just initializing with the wrong initial condition, because for the scattering problem, what is a scattering? Scattering means that you have some particle that is propagating in the vacuum for a long time. Then there's a finite size target, it goes to the target, and then it again propagates in vacuum for as long as it likes, and then it's detected in a detector meters away. So meters is just like an infinity away. So this means that to study a scattering problem, we need to not start with a pure quark state, but we need to start with a true asymptotic state. And a true the physical quark state, a true the state that corresponds to a physical quark scattering is not a pure quark state, but a physical quark has its cloud of gluons that it develops while it's propagating in vacuum for an infinite distance before it comes to the target. So in order to study a physical scattering, we need to not have quark and gluon states, but we need to find the actual physical states corresponding to a physical quark and a physical quark gluon system. And which we are basically here, somehow this is a non-perturbative formulation. You can find these perturbatively, but in our case, we can find them also non-perturbatively. We have a Hamiltonian. And so what these physical true asymptotic states should be are the eigenstates of the vacuum Hamiltonian. So the Hamiltonian with the gluon emission and absorption, but without the background field. So basically what we're doing is constructing, partially analytically, partially numerically, the eigenstates of the vacuum Hamiltonian. So emission and absorption. So these eigenstates will be superpositions of quark and quark gluon states. And in order to calculate a meaningful scattering cross-section, then we're going to have these state, such an true asymptotic state come in, interact with the background field. Then the background field stops, and then we have to project out again to the true asymptotic states to get the real cross-section. This is what we're working on now. Jet quenching, I think the problem of jet quenching is something that you guys know better, much better than I do. In some sense, what one would want to do in the jet quenching problem is that I have an incoming quark, maybe, which is not maybe an asymptotic state, but it's something that is created inside the medium from some hard scattering, which is kind of this hard scattering, which is somehow external to our problem. What we would want is that we have a quark that is inside the medium. It's just born out of some hard scattering that happens so fast that we don't care about it. Then what we want to do is to follow the quark. And then, for example, I would like to use this to understand how to understand really explicitly this question of, for example, radiative corrections to Q hat. But what somehow still needs to be done, I think, is we need to do, or we need to find from somewhere what would be the proper way of formulating things. What would one want to use this for? And if there are good ideas, I'm very interested in hearing them. So far, currently, we are working on the scattering problem, but somehow I would like to, if there's a way for this code, this way of calculating to be useful for something in jet quenching physics, to maybe get a non-perturbative result for something that is only non-perturbatively, or somehow just to explicitly demonstrate how something is happening. That would be very interesting. But the problem for me is that I know less. I'm not 100% sure of how I should formulate the calculation that I should be making. Good. But that was all I had. Thank you.
Yeah, thank you very much, Toumas. And are there any questions?
So I have a question, of course. Well, I think one kind of interesting thing. So we did something with Johannes recently, one of my PhD students here present. So we kind of in the jet quenching. Well, it's kind of, or it could also be for the other case. I mean, what you would end up with is some kind of at any time propagating through the medium. So it was mostly for the jet quenching case, but at any moment propagating through the medium, you can define some kind of a color singlet state. Okay. But this is, of course, on the level of the amplitude and the complex conjugate amplitude. Exactly. So we have basically our process in the amplitude and a complex conjugate amplitude, and we have some kind of like a Schwinger-Keldysh combination of the two sides. And then at any point in propagating through the medium, we have basically a correlator of several particles. And so how does this picture relate to yours? I mean, so in the end, in your case, you're only kind of dealing with the
we're only dealing with the amplitude in some sense.
And then
then the complex conjugate is, I mean, you just take the complex conjugate and square. And
right, so the complex conjugate, well, okay, so you're basically,
because you have an amplitude, you explicitly have an amplitude, right? And you can always, you can, complex conjugation is just flipping some signs.
Yeah.
The question is, one thing that we have been somehow more applied both to this case and but even more generally is that Magian has also been, or Magian has been learning how to do the color algebra. Of course, here now, right now, here our starting point is not a singlet; it's a quark state, so it's not a color state. Then somehow the quark gluon, if you just emit in vacuum, you get a quark gluon state which is in the triplet representation. But it's really, there are 24 color states altogether. There's a 24 color states, which is, how did it go? There's a decuplet, and there's the anti-sextet is a triplet anti-sextet, and triplet anti-sextet and a 15. There's a 3, 6-bar, and 15 are the possible color states of a quark gluon system. In vacuum, you can only go, a quark can only become a triplet quark gluon system. But then you're exchanging color with the medium, so you can go into a 6-bar and a 15. And I don't know, one way of somehow maybe at least a new way of thinking about all of this physics would maybe to think in terms of the total color of the two-particle state, or more generally of the multi-particle state.
Yeah. So that's basically what we see with there is that kind of your, which is kind of puzzling. So we were thinking about how to extend that. So basically, you see that your state, exactly this state that you ultimately want to project to, which is the vacuum state that you basically measure in the end, decays away, right? And you know, because it decays away because you somehow fill it, you get projected into color states which you won't measure, let's say like that.
Yeah. Well, I don't know, why don't you measure them? Because somehow, of course, this color state correspond to perfectly, if I'm thinking of the quark to quark gluon, these color states are perfectly possible color state for a quark gluon coming out. They're just not the same kind of color states that the single particle could have.
Yeah. So
they are color states that could, I mean, physically can be produced.
Well, perhaps, yes. So perhaps you could, perhaps you could think about projecting them onto all possible color states of a two-body system, right? Or consisting of a quark and a gluon, or two quarks, for instance, or two gluons, right? Yeah. But then what's interesting in your approach is that you still have the initial quark as well. So also, I mean, explicitly you conserve probability, right? So
yes.
So it's quite nice. Nice startup, yeah.
So I think it's kind of in some sense an explicit first principles approach, that I mean, you have everything. Now for the problem of jet quenching, my problem is that I'm not exactly sure what I should be calculating with this. What's the definition of the observable that I would want to calculate? Right.
So one interesting thing it would be, right, is this standard by now standard kind of idea of Al and Bin, and then later Yassine and Jean-Paul, is that first of all you start out with the quark and you measure kind of its trajectory, right? That will give you the bare Q hat. So basically your cloud, how it grows, right?
Yeah.
And then adding in the gluon state and basically removing and integrating out the gluon, right? Somehow, in some way, would give you kind of the radiative correction to that. So you would basically have a gluon. It could be radiated, but you never measure it, or you have the virtual correction, of course. And from that you get kind of so that would give you kind of how your cloud would grow, from just first of all from the bare quark, and then having this QG state.
Yeah, so,
right?
so I guess the Q hat you would really measure as a total transverse momentum gained by the state by in a certain period of x plus.
Exactly.
And so then you can do the calculation where just the quark is propagating without being allowed to emit gluons. It will a certain field, it will accumulate a certain amount of transverse momentum. Then you have a quark gluon system that you're allowing to propagate. And then, of course, the quark gluon system will get more kicks from the same color field. So it will gain more transverse momentum. And then, of course, somehow this quark gluon system just needs to be, I guess, in that case, one actually would be also looking at such an asymptotic state. Namely, that one would actually be taking a superposition of quark and quark gluon states, which corresponds to a physical quark with its gluon cloud.
Exactly. And exactly, and then what they found, right, is that this length dependence, so how this cloud grows, how the dispersion grows, doesn't grow linearly with L anymore, right? It grows with some power of L. 1 plus or minus gamma or something like that. So it grows faster than L basically. And that's because of this additional sensitivity. By having the gluon cloud, you get an additional sensitivity because so it seems to be quite nicely
I guess that is something that we should try to somehow figure out how to formulate it, and one could calculate this explicitly.
No, it would be it would be very nice. I mean, this is a very nice formulation because it's so, as you said, textbook amenable to textbook insights, so to speak. But really it is this, right? So usually, in perturbation theory, we really think about these bare states, but as you say, I mean, you have all these hardcore fog kind of, all this cloud is really there. So maybe it would be cool to think a bit about this problem.
Okay, so thank you, Toumas, for your talk.
Thank you.
And thank you for the questions for everyone. And I think that's all for today. And we are looking forward to see your next papers.
We're trying to get it out soonish, maybe not. At least we're trying to get most of the stuff done before Bergen goes to Santiago. Might take a little bit more to write the paper, write up the paper.
In January, right?
In January,
Cool.
Okay.
Thanks a lot, Toumas.
Okay,
thank you, everyone.
Bye-bye.
Bye.